Imagine holding just a few pictures of a scene, say, your living room, or, I don't know, even your car. Now, picture this. You can instantly generate a pretty much flawless 3D model of that entire scene, and you can view it from any angle you can think of, even perspectives that were like completely hidden in your original photos. This isn't just about making cool visuals for games or whatever. It's a really fundamental leap in how AI understands and reconstructs our complex 3D world from, well, pretty limited 2D information.
Yeah, it's really about going beyond just what's seen in the photos. It's about grasping the underlying structure, the shape of reality almost, enabling the AI to intelligently, hallucinate plausible content for parts of a scene it has actually never observed before.
That really is the dream, isn't it? And today we're taking a deep dive into a groundbreaking new framework that's genuinely pushing the boundaries here. It's called Aligned Novel View Image and Geometry Synthesis via Cross-modal Attention Installation, which thankfully everyone seems to be calling MoAI.
And our mission today really is to unpack the significant challenges. I mean, these are persistent problems in creating truly realistic 3D scenes just from a few 2D images. And then we want to explore the really innovative ways MoAI tackles these hurdles. We'll dig into its core breakthroughs, especially how it generates parts of a scene you've never seen before, while keeping both the generated images and their underlying 3D structure, perfectly aligned. That's the key.
Okay, let's get into this. Because novel view synthesis, NVS, has been super exciting, but yeah, it's definitely hit some roadblocks. What's the first big problem people ran into?
Well, one of the primary obstacles is what researchers often call the extrapolation hurdle. A lot of existing methods, think like early NeRFs, neural radiance fields, or maybe 3D Gaussian splatting, they're actually brilliant at reconstructing areas that are visible in your input photos. They're masters of interpolation, you could say. Really good at filling in the gaps between what they've already seen. They make smooth transitions, high fidelity.
Right, so if I feed it pictures of my car, front, sides, top source, it can rebuild those views perfectly. And I can smoothly move around those known areas. But if I try to look underneath the car, an angle it's never, ever seen, it just struggles, doesn't know what to put there.
Exactly. They fundamentally lack extrapolation capabilities.
Oh, no.
They really falter when you ask them to synthesize areas that are completely occluded or unseen from those reference images you gave it. And this is the point where the model isn't just reconstructing based on input. It needs to, hallucinate plausible scene content. It has to make a really good guess about what should be there. So for you, trying to peek around an object into an unobserved space with those older methods, you'd probably get blurry results, inconsistencies, maybe just weird artifacts.
There's a bit that makes a lot of sense. So, okay, struggling with unseen areas, that's one major hurdle. Were there other big issues holding NVS back?
Oh, absolutely. Problem number 2, you could say, came up even with newer generative methods, things like 0123 or MV-Dream. Now, these can extrapolate to some extent, which was a step forward, definitely, but they often needed known camera poses as input, and maybe more critically, they were often limited in synthesizing novel views at arbitrary out-of-domain viewpoints. Basically angles or perspectives that were just very different from what they saw during training.
Oh, okay. So they could generate some new stuff, but only if it was kind of similar to their training diet. Like if they only learned from eye-level shots of cars, they'd struggle with a dramatic drone shot, maybe even of a new car.
Precisely. So for the user, it meant you gained some generation power, but you might still be stuck with only certain types of angles, not that truly free go-anywhere movement. MoAI, on the other hand, really aims to work from unposed input reference images. You don't need to know the exact camera positions and generate truly arbitrary viewpoints. That's a huge goal for flexibility.
Okay, now this next one seems like a really fundamental challenge, and I bet it caused a lot of headaches. The misalignment between the image and the geometry. Why is that such a big deal? Why don't they just naturally sync up?
Yeah, this is a core problem. Think about methods that use warping and inpainting. They take some initial 3D data, project it to the new view, and then basically use image editing techniques, inpainting, to fill in the blanks. These often really struggle when the viewpoint change is large. Why? Because they're mostly relying on 2D image inpainting. They lack that deep, comprehensive understanding of 3D structure. And MoAI makes this really critical observation. Just feeding the same raw info to both an image network and a geometry network, it's simply insufficient in achieving alignment. Images and 3D shapes, they just capture different things: texture, color, fine details versus spatial layout, depth, form. They behave differently.
Wow, okay. So you can't just give them the same dictionary and expect them to speak the same language, basically. They need a more deliberate connection. That sounds tough.
It really is. And adding to that difficulty, problem number 4 is just the practical reality of noisy and incomplete geometric inputs. The tools people often use to get that initial 3D data guess from images, these off-the-shelf geometry predictors, they're not perfect, far from it sometimes. They often give you a sparse 3D point cloud, think like a loose scattering of dots in space. And it's often filled with noise and errors, especially if your target view is really different from your input views. So for you, the listener, if that initial 3D data is messy, your final scene is almost certainly going to inherit that messiness. The whole process builds on that foundation.
Right. It's like trying to build a perfect sculpture, but your initial block of marble is full of cracks and missing chunks. The end result is compromised from the start.
That's a great way to put it. And then there's a 5th issue, maybe more subtle but still important. The scale shift discrepancy in depth prediction. This is a common headache where the predicted depth, how far away things are, might be consistently off. Maybe everything's predicted as 10% too close or shifted back by a certain amount. It's an inconsistency of depth scale and offset. MoAI tackles this partly by thinking of it as a completion task, filling in missing depth rather than just predicting raw depth values from scratch. That helps stabilize the scale.
Okay, wow. So 5 pretty significant challenges: extrapolation, arbitrary views, that crucial image geometry alignment, noisy inputs, and depth scale issues. This is where MoAI comes in and really makes its mark, right? Especially with that alignment problem. This sounds like the core innovation.
Absolutely. This is the heart of it. MoAI introduces this technique they call cross-modal attention installation. In simple terms, it's a way where the spatial attention maps, basically, where the image network is focusing its attention, are literally taken and used to replace the attention maps within the geometry network. This happens during both training the model and when it's generating new views.
Hold on, attention maps. Can you break that down a bit? What does it mean for an AI to pay attention?
Think of it like the network's internal spotlight. When processing an image, an attention mechanism helps the network figure out which parts are most relevant for the task at hand. Like, this pixel here seems important and relates to that pixel over there. These attention maps show those relationships and areas of focus. So MoAI essentially takes the image network's understanding of spatial relationships. This part of the couch corresponds visually to that part and injects that understanding directly into the geometry network.
Ah, I see. So you're telling the geometry network, hey, pay attention to these structural relationships that the image network has figured out.
Exactly. You're guiding the geometry network using the visual system's focus. And this is brilliant because it creates this synergy, these mutual benefits.
Okay, tell me about those benefits. How did the two networks actually help each other out here?
Well, first, think about the image side. The researchers found something really interesting. Geometry denoising significantly outperforms image inpainting when you have large missing regions. Why? Because figuring out a consistent 3D-shaped geometry completion is inherently more deterministic. It's often easier for the AI to define a solid surface than to perfectly paint in complex, unknown textures and lighting over a large blank area.
So the 3D understanding is actually more robust, more reliable, when you're guessing big chunks of unseen stuff.
In many cases, yes. So the image network, the part doing the painting, it receives deterministic training signals from the geometry completion network. It gets this strong, clear guidance about the underlying structure. This really regularizes its generation process. So for you, it's like our artist, the image network, gets a super accurate 3D blueprint from the modeler, the geometry network. This helps the artist paint even the unseen parts much more consistently and realistically. It enhances consistency and in-painting capability.
That makes perfect sense.
Yeah.
And it works the other way, too.
Yeah.
What does the geometry side gain?
It does. Conversely, the geometry prediction network leverages rich semantic features from the image domain. Images are full of context clues, textures, colors, object recognition cues. Knowing that a patch of pixels represents grass or brick or tire rubber helps the geometry network infer much better shapes and boundaries. So our 3D modeler, the geometry network, gets access to all the rich visual details and semantic understanding from the painter, the image network. This helps it refine its shapes, making the final 3D structure much more accurate and realistic.
And you mentioned it avoids harmful mixing. What's that about?
That's a really crucial detail. The information transfer uses only the attention maps. It uses them as structural information for aggregating value features. It specifically prevents the harmful mixing of features from different modalities. You don't want, say, raw pixel color values messing up the calculation of 3D coordinates. This keeps the collaboration clean and effective. Each network shares its spatial understanding without corrupting the other's core data type.
They had that example with the wheel, right? That really drove the point home for me.
Yeah, exactly. When trying to complete a partly hidden wheel, the image model alone struggled to figure out the full shape. It didn't have enough visual cues in the missing area. But the geometry model, understanding 3D shapes, could correctly attend to other wheel locations on the object for structural reference. It knows wheels around, and there might be similar ones elsewhere. By injecting that geometry-based attention into the image network via MoAI, suddenly the image generation quality for the wheel dramatically improved. It shows how that shared structural awareness makes a huge difference.
Okay, so cross-modal attention installation is definitely the star player here. But MoAI also builds on other smart ideas, right? Like revisiting that warping and inpainting concept.
That's right. It doesn't throw out existing ideas, it builds on them cleverly. It starts similarly using off-the-shelf geometry predictors, things like DUST3R or VGGT, to get that initial partial 3D point cloud from the input images. These sparse point clouds are then merged together and projected to the target viewpoint, basically oriented for the new view you want.
But the MoAI twist is applying this inpainting idea, not just to the image, but to the geometry itself, and handling multiple views.
Precisely. It frames the whole problem as an in-painting task for both image and geometry. You're filling in the blanks in the picture and filling in the blanks in the 3D shapes simultaneously. And a nice practical benefit they point out is scalability. The architecture can receive an arbitrary number of input viewpoints. You're not stuck with just one or two input photos. Their experiments show that performance really benefits strongly from additional viewpoints, even if the model wasn't specifically trained using that exact number. So more data generally helps.
And then there's the proximity-based mesh conditioning. This sounds like the fix for that wobbly bricks problem, the noisy initial 3D data.
Yeah, this is how they handle that imperfect starting point. It's quite neat. First, it takes that sparse point cloud, the scattered dots, and converts it into a mesh representation using a ball pivoting algorithm. Think of it like stretching a skin over the points, connecting them into a surface. This makes the geometric information denser and more interpolated, less just floating points.
Okay, so turning the dots into a sort of preliminary surface. Makes sense.
Right. Then, this mesh information, specifically its depth and normal map surface orientation, is used to augment the correspondence condition fed into the networks. It gives richer geometric cues. And here's a clever filtering step. It applies normal masking. It essentially ignores parts of that initial mesh whose normals deviate more than 90 degrees from the target viewpoint's direction. These are often surfaces facing away from you, or just errors from the initial projection. Masking them out stops them from confusing the generation process. So for you, it's like having a smart filter that cleans up the initial 3D guess, ensuring only the most reliable geometric hints guide the final output.
Okay, this is getting technical, but it sounds crucial. And there was one more. You called it an unsung hero. Camera space, point map, normalization. Why is this detail so important?
This one's subtle, but addresses a real pain point in training these kinds of models. The problem is, if you work with 3D coordinates in world space, their actual position in the scene, the model has to deal with huge variations. Think about objects being really far away versus right up close. The model has to handle these dramatic variations in absolute coordinates while also trying to learn the subtle geometric relationships, like the exact shape of an object's surface. That's a lot to juggle. Handling massive scale differences and fine-grained detail simultaneously can really hinder learning.
Right, like trying to measure millimeters on a map that spans continents. The scale difference makes precision hard.
Exactly. So MoAI's solution is elegant. It transforms all predicted point map coordinates values into the target camera's local coordinate system. Everything gets recentered and scaled relative to the viewpoint you're trying to generate. The benefit, it eliminates this burden. It creates a unified coordinate frame. The model can then focus its entire representational capacity on just understanding the geometric patterns and correspondences, the shapes themselves. This leads to more stable training and a better ability to synthesize geometrically plausible novel views. It simplifies the learning task significantly.
Okay, theory and clever techniques are great. But how does it actually perform? Does it deliver in practice? The proof is in the pixels, right?
The results they show are really quite strong, especially in those tough extrapolative settings we talked about. MoAI achieves state-of-the-art performance in extrapolative camera settings. For example, on the real estate 10K dataset, which has complex scenes, it got a PSNR score, that image quality metric, of 17.41. Competing methods were down around 14.0 to 14.4. That's a noticeable jump in quality.
Wow, that's not a small improvement. That's quite significant for these kinds of
It
metrics.
really is. It's much better at hallucinating plausible scene content for those unseen regions, filling in large missing areas where older models just kind of give up or produce mush. And critically, it produces geometrically aligned colored point clouds. The 3D structure it generates matches the image it creates. You don't need extra steps like optimizing a NERF or 3D GS afterwards to try and fix the geometry. MoAI produces both aligned image and geometry directly.
And without generalization, can't handle data it's never seen during training. That's always the acid test.
It performs well there too. They show superior performance on the DTU dataset, which was importantly not used during training for any of the compared models. So that demonstrates good zero-shot generalization. It also seems robust to noise. It can effectively filter artifacts and noise from predicted point clouds during warping, meaning even if the initial 3D guess isn't perfect, it still produces clean outputs. And beyond the visuals, it also significantly reduces depth prediction error, leading to more accurate depth maps with smoother transitions, especially around occluded areas.
Okay, impressive results. But good science means proving why it works. Did they do those ablation studies, taking parts away to see what breaks?
They did, yes. Rigorous ablation studies are included, and the results clearly show that each key innovation we discussed, the point map conditioning, the mesh conditioning, and especially that cross-modal attention installation, each one progressively improves performance. It rigorously validates that all these pieces work together and contribute meaningfully to the final breakthrough performance. It wasn't just one lucky trick, it's a well-designed system.
So let's pull this all together. We've seen MoAI as a really big step in novel view synthesis. It tackles image and geometry prediction together. It uses that clever cross-modal attention to make them help each other, handles noisy data smartly, and deals with those tricky extrapolation cases much better. It's overcoming some really long-standing hurdles.
It really is a powerful combination. It addresses the core challenges of getting geometrically correct, good-looking views from just a few pictures, especially when you need to see around corners, so to speak.
Thinking bigger picture then, imagine what this enables. Truly dynamic digital twins of real places. Hyper-realistic virtual tours made instantly from a few phone snaps. If AI can now reliably, hallucinate accurate unseen 3D reality, what does that unlock? Augmented reality, virtual production, maybe even a robotics navigation.
Yeah.
What stands out to you as the most exciting potential impact here, generating this unseen reality?